Okay. Okay, 1 second. Admit it, you would want David to sing more than you want to hear me. I know it. I know it.
Wait a minute, we gotta make sure we get a Silva filming. Where's Patrick?
He's right there. Yeah, it's all good. It's perfect. Thank you. So actually, quite a lot of exciting updates. Quite a lot of exciting updates this last year. How much louder can I do? I've got a microphone. Uh, um, I um, I think we've got a lot of fun things that have happened this year, so I hope you're all adequately liquored up to hear this mostly good news, except the fact that I've lost a good deal of hair since I last talked to you, I think. So that's the big difference. Got an extra chin, but but the rest of it is all good news. So I'm going to update you a little bit. I'm going to take I think most of you are pretty familiar with the stuff that we're doing. Is anyone new this year? Okay, so we've got a few new people. So I'm going to take you through a couple of things. I won't take too much of your time, but I hope you'll find this exciting. Before I start, obviously, goes without saying, I'm so grateful to David, to Paul, to the Silva family. Thank you so much. In great and loving memory of Veronica and Mark Silva. And I want to thank Lauren and Devon as well from the Brigham, without whom this couldn't happen either. So thank you all very much for making this possible. All right, so a little bit about this condition, Joseph's disease. In many ways, thanks to the Silva family, this disease, as most of you know, came over to New England from the Azores, from the Portuguese fishermen. There was a founder effect. The original founder was actually examined by my predecessor, David Dawson, at the Brigham, who named the disease some years ago Machado-Joseph disease, or spinocerebellar ataxia type 3. Now, until the Silva family, I think, were courageous enough to make this public and destigmatize it, this disease was largely under wraps in New England. We would see patients from around the area, but no one would really talk about the disease. So I really, really thank the Silva family for their courage in destigmatizing this disease, because that's the first step to finding a cure. So thank you. So there are some common themes here, like Alzheimer's and Parkinson's disease, that are very common. Spinocerebellar ataxia type 3 is also a disease where the proteins clog up brain cells. And that's a common theme. That doesn't mean that one treatment's going to treat all these diseases, but there are going to be some common themes. So the work that we're doing here is going to influence the work other people are doing on Parkinson's. The work people are doing on Alzheimer's is going to influence the work we're doing here. So we're all helping each other with this. Now, what happens here is there's a mutation in the gene. That's why typically 50% of people in an affected family for every generation get affected. That this is quite brutal because there's this change. And what this change does is it leads to a clumping up of proteins, and eventually the neurons in the brain, the electrical cells, degenerate. Now, something that's going to be really important in today's talk is that it's not just happening inside the cells. There are a lot of brain cells, and just like you get inflammation when you hurt your finger, you get inflammation when you hurt your brain. And the inflammation may be critical in driving the progression. We think these diseases start early in life, and only when you've lost quite a few neurons do you come to see the neurologist. So by that time, the brain has changed a lot, and there's a lot of other things going on, like inflammation. So this year, we're going to talk more about inflammation, and that, we think, also is a big part of causing this neuronal loss. Now, a little bit of neuroanatomy for you so that you understand my talk. This is the brain. The eyes would be over here. This is the front of the brain. This is the back of the brain. Down near the back of the brain is a part of the brain called the brainstem, and marked here in the darker color is a part of the brain called the cerebellum. It's the cerebellum that you're all affecting tonight by drinking, okay? And so you know, it's the piece of the brain that makes you fail the sobriety test, but it's also the part of the brain that gets affected in ataxias. Now, there are other parts of the brain, and I'm glad David mentioned that he and Veronica took a drug called dopamine. You might as well, levodopa he called it. You might wonder why it is that Veronica and David took dopamine. That's normally something you give to patients with Parkinson's. That's because in these ataxias, there's also an effect on the same brain cells that are affected in Parkinson's. But ataxia patients look very different to Parkinson's because there's two things going on. So they're on top of each other, so that's why they look very different. But at the brain level, there's another part of the brain called the midbrain that's affected, where these neurons that secrete dopamine are affected. So when Veronica's voice and David's voice started getting softer, we started thinking about giving them dopamine, and fortunately that has helped their voice, as you heard. Okay, so that's the anatomy you need to know. The other thing, for those of you who are new this year, you would know that one of the things that the Silva Foundation has supported us to do is to create the first human stem cell models of spinocerebellar ataxia. We've been working on this for years with you, and we have been able to distribute the stem cells that we originally made from little tiny pieces of skin from Mark and Veronica. Those stem cells have been distributed across the United States to further research into Joseph's disease. So what is, these are called iPS cells. What are they? It turns out that we can take a little piece of skin, hair, even a urine sample, blood sample, and we can turn those adult cells back in time so they look just like embryonic stem cells under the microscope, and we can grow heart cells from them, brain cells, gut cells, and even mini brains, little versions of our brain in the lab, which we do routinely now. So this is the basic idea. Here's a person, we take skin cells, these are called fibroblasts, we turn them into these iPS cells that look like embryonic cells, and we can grow brain cells and then use those to study the disease and to develop new drugs. Okay, and we've been talking to you about this journey for a long time. My wife, who's here, and I made some of the first human stem cells 15, 16 years ago from patients with Parkinson's disease, and those have led to new drugs that are now under development from other companies. We want to do the same for Joseph's disease, and the learnings, as I said, from those diseases is going to help us. So that's the basic idea. I haven't said anything yet. Thank you, though, but the better stuff's coming. So we have developed at Mass General Brigham, we've developed a very exciting, based on this 15 years of work, we have developed, and we have now, and this is really big news, we've made a splash with a program called MyTrial, which has attracted a lot of interest in the Parkinson's and the common disease world. And I want to share with you that the infrastructure for MyTrial has now been funded to the tune of $10 million for the next 5 years. But you know, it could not be done without all of the support that we've had from people like you. And even now, MyTrial, those funds don't support ataxia research. So what you have done here is allow us to build on what we've done in more common diseases, but apply them to ataxias. There are 2 Silva Ataxia Foundation Fellows, 2 junior faculty members at Mass General Brigham who are now starting their labs in ataxias because of you guys. And so that's going to propagate, okay? Yeah, it's really very, very exciting, and it's the biggest thing we can do is really build the next generation of researchers. So what is MyTrial? So MyTrial is a program where we take patients like David and Paul and other patients with Parkinson's, we deeply follow them in the clinic, and then we prepare them for a drug trial. But we do something really important. We treat them, and we also treat the brain cells that we make from them in the lab. So by that, we start to understand who responds to these drugs, who doesn't respond. You know, that's how they test cancer drugs, right? And target them to the right patient. We can now use these mini brains in the lab to target the right drug to the right patient. So there's two really important ingredients of my trial. There's making the stem cells. I just told you about that. But what do we track in the brain, right? How do I know that I'm following the same thing in someone's brain that I'm following in their brain cells? We use something called PET scans. Has anyone heard of a PET scan? Okay, right. So this is a scan that doesn't just tell you about the structure of the brain, it tells you how the brain is active. So we make PET markers so that we can see the same things light up in the brain that we're looking at in the dish. And then when we give the drug to the brain and to the mini brain, we can figure out if we're getting a match. That's the idea of my trial, and we're very excited about the program. So that's what it shows here. You make the stem cells, you follow the patients, you do a PET scan, you make human stem cells in the dish, you figure out who doesn't respond, who responds, and now you can make a really smart clinical trial. You're not worried about the fact that one patient with Joseph's disease could be different to another patient, so one drug could be good for patient one drug could be good for patient two. You can figure it out before you put them in the clinical trial. You save time and you match the right drugs to the right patients. We hope this will be in time a game changer for neurodegenerative diseases. Okay, so I'm going to follow 4 quick themes based on what I told you about last year. First, can we connect patients with Joseph's disease to new treatments? That's number 1. Number 2, it's really hard to make mini brains from the part of the brain that I told you about that's affected in Joseph's disease called the cerebellum. And so we're collaborated with the University of Southern California to do this from Silva family stem cells. I'm going to show you the first data from that. 3, can we create new gene therapies for patients with genetic ataxias? I'm going to give you a great update on that. And 4, can we treat brain inflammation? There is a drug that's been invented. It's very exciting. It was invented at Mass General Brigham. I have no, by the way, financial interest. I've never had anything to do with the development of that drug, but I saw how interesting it was in treating brain inflammation. It was originally designed for multiple sclerosis. So this year we asked the key question, could this drug potentially be useful for patients with Joseph's disease? So I'm going to share very quickly these 4 updates. So as David mentioned, he and Paul and other patients with Joseph's disease in the New England area are now welcome to come to Mass General Brigham to get access to a new drug. And this drug was developed by Biohaven Pharmaceuticals. And last year they showed, very excitingly, that there was potentially a 50% slowing of the progression of the disease with this drug, which is huge. Now, for a really rare disease like Joseph's disease, it's really hard to gather hundreds of patients and give some of them a placebo and some of them the drug. So I want to be clear, there is something very creative about Biohaven, but also a little risky. For this drug trial, they used historical data of how much we were expecting these patients to progress. So this is going to be a huge test in the next month. We will hear from the FDA on whether they are going to approve this drug or not approve it. This would completely change the way approvals are done for all neurodegenerative diseases, and we're just not sure if they're going to approve it because these people who didn't get the drug weren't in the actual trial. They were historical control subjects. So I hope it's approved. It's a very strong result, but we're going to have to see what the FDA does, okay? But before waiting, we still wanted our patients to get access to a drug that is potentially helpful. So the team made this possible, and I'm really grateful to patients like David, Paul, and others we just heard in the room who are coming to Mass General Brigham now for this drug, and fingers crossed that it helps them. This is just a slide, just so that you all keep tuned in the next few weeks. This was a story just this week in Stat, where they're talking about this very drug for Joseph's disease, and you can see it's getting a lot of attention because we're all waiting what the FDA says. Okay, so now I'm going to move to the second update, stem cell models. Incredibly hard to make cerebellar mini brains in the lab. This is a very, very difficult thing to do. Georgia Quadrado was a trainee at Harvard University in Paula Allotta's lab. She's a very talented stem cell biologist. About a year and a half ago, she had this beautiful paper saying that she could make these mini cerebellums in the lab. And so I became excited. I asked the Silva Foundation whether I could support her, and thank you to the foundation, we were able to support a graduate student and a postdoc in her lab to take Mark and Veronica Silva's cells that we had genetically corrected and start to make the first cerebellar models of Joseph's disease. And this is Georgia here. We also sent the same cells to Hank Paulson at the University of Michigan, but I'm going to talk about Georgia's work today. So this is the part of the brain I showed you before, and this is why it's so hard to make these cells. These cells in the cerebellum are unbelievably complicated. Each one of these brain cells, believe it or not, connects to 50,000 other brain cells. Just one of those cells. So they're very, very difficult to make. So I'm really thrilled. We don't need to go through how they do this, but I'm really thrilled to show you the first mini brain models from Veronica and Mark Silva that were made from, this is from Mark's cells with the mutation. This is with the mutation corrected. These are growing now in their lab, and I think this is a landmark achievement that will make a big difference to studying this disease. And really, this is early data, so this is just the first couple of experiments, but there's something remarkable. You will know, some of you who've been coming here for years will know that for several years my lab worked on genetically correcting the mutation in Mark and Veronica's cells. It was a huge undertaking. But what it means is we can take Mark's cells that have the mutation and compare them to Mark's cells without the mutation. That's the perfect way to figure out what that gene is doing, because if I made stem cells from everyone here, they'd all be different, right? So how would I know what the ataxia gene is doing? So the first experiments that they've shown have been remarkable. Does anyone see the difference between the cells that have the mutation and the one with it corrected? One of them's bigger, right? And we know that there's no difference in proliferation, which means that the cells in this one were surviving more than the cells in this one. This means for the first time, labs have a way to measure the difference. This is the sort of thing you can now develop drugs around. So if they can repeat this and get much deeper in the coming year, I hope that these pathologies in brain cells are going to be a game changer for how we discover drugs or test genetic medicines in this disease. So I think this is a really spectacular result.
Okay, folks, it's 8:15. If you want to speak to the back of the room, make your final bids. We're going to collect the...
Sorry, I'm ruining... Sorry. I'm ruining your auction. Okay. Self-defeating. But anyway, if you don't mind, I'm going to tell you a couple more things. Is that okay? Yeah. Is that okay? Okay. All right. I think this is really cool. Okay. So I'm trying to get through. This is Silva Ataxia Foundation Fellow number 1, Asha. She's an assistant professor at Harvard. She is working on developing new gene therapies for ataxia. And for those of you who've come in the last few years will know that the first patient that we tried was a young boy who has an ataxia. It's not Joseph's disease, but it's very closely related. It's called Derpler. So he was really young and he was really progressing fast with ataxia and seizures. We decided to team up with colleagues at Children's Hospital and Ionis Pharmaceuticals to develop a gene therapy and make his stem cells. Okay, so last year I told you that we had made his stem cells and that we were starting to see abnormalities in them. Remember, he gets seizures. Does anyone see the difference between the cells on the left and the cells on the right? Those cells on the right are brain cells that we have growing in our lab, and they're having seizures in the dish, okay? And what was remarkable was we could correct the seizures with a gene therapy, And 18 months ago, I told you this had started last year, we started giving him that gene therapy, okay? So it only took us 3 years to go from a stem cell testing and making the gene therapy and getting it into the patient, okay? Because he progresses so fast, there was a thought that maybe we could slow his disease down and we could actually figure it out. What's remarkable is if you look at his old seizure activity, it started off like this, where it was in one spot. It became very general and severe. And then in February, he got the treatment. And can anyone see that there's now a change? I don't want to overpromise, but it's a very intriguing change that we are starting to change his seizure activity with this drug. It's very hard to prove this in one patient. But what's really exciting, just last week, I don't have that slide. But I'm going to tell you, just last week, we had a meeting, and what has happened is, over the last 3 months, he's had his first seizure-free months. He normally has seizures every week. And not only has he had less seizures, but his doses of his anti-seizure medicines have come down by more than half. So we really think we're helping him. I don't want to overpromise, but it's exciting that we're able to do this. So that's Usher's work. Okay, so now the last part of the talk is can we make a drug for inflammation? All right, I've told you inflammation could be a really big part of why these diseases progress in patients who've already got symptoms. So this is Howard. Howard Weiner is really a pioneer. He lives in Boston. In fact, there was the Howard Weiner Symposium today to honor 50 years of his work. He has been behind the development of most of the drugs that you see for multiple sclerosis, and he developed nasal furalalimab. Nasal furalalimab is a spray that is in clinical trial for multiple sclerosis and in clinical trial for Alzheimer's disease. It changes T cells in the blood, and they cross into the brain and they dampen down brain inflammation. It's a very clever drug. So I want to say that even though I'm not going to show you this in so much detail, my group talked to Howard. We've been working for a couple of years on this, and we drugged the first patients with multiple system atrophy, another ataxia, in August with nasal furalalimab. So we've given them access to the drug. And the reason we could do that is because we found very strong evidence of brain inflammation with a PET scan. So last year I left you with this question: is there going to be evidence of brain inflammation? No one knows. Is there evidence of brain inflammation in Joseph's disease? And David and Paul, and I talked to them last night to get their permission to share their information, but David and Paul were brave enough to launch themselves into this clinical trial so that we could study this. As both of them know, it's not easy to get these PET scans organized. Sometimes Paul would show up and we'd say the scanner has failed, and poor Paul would have to come all the way back to the Cape. It was absolutely terrible. This is research. But we managed to get and analyze their scans. And I want to show you those with their permission. This is work, by the way, from Widad Abuchar, who is a phenomenal young neurologist and instructor at Harvard Medical School. Thanks to you, she's the second now Silva Ataxia Fellow, and she's studying brain inflammation. This is a close collaboration also with my friend and colleague Tarun Singhal, who does all the PET scanning for us. So I want to show you something really remarkable. This is the front of the brain. This is the back where this is the cerebellum where we were making those stem cells from. And can you see these red splotches? This is brain inflammation. And you can see this in the back of the brain, in the top of the brain very clearly, in both Paul's scan here and in David's scan here. This is the first image of brain inflammation that's widespread in the brain of patients with Joseph's disease. This means that I hope with your help, will open up a completely new avenue for thinking about treatment for this disease, not just the gene, but also the inflammatory response to the neuronal problem that gene causes. Does that make sense? So we think this is very exciting, and we're going to now examine David and Paul and other patients, thanks to you all, we've got more than just this family. We're able to scan other patients, and we will now see in the next year, does this progress? Because if it progresses, it means it's getting associated with their symptoms, and then I am going to apply to the FDA for an IND, just like I did for multiple system atrophy patients, so that we can get approval for nasal furalumab for Joseph's disease. So I don't want to take more of your time, but we're really, with your help, and thank you for all coming, we want to continue all of this great work. We want to continue the clinical trial work of troriluzole and furalumab. We want to keep studying with our collaborators inflammation in the stem cells of the brain. And I want to continue to support the development of gene therapies for these diseases so we can rapidly match the right drug to the right patient at the right dose so that we know we're benefiting the patient and not causing harm. So with that, I thank you very much for your time.